Hello everyone, my name is Atul Acharya and I will be presenting my FIP project titled Query Cost Estimation with Deep Learning. So most commercial database management systems consist of a very vital component called the query optimizer, which is responsible for executing a query in as little time as possible. The query optimizer consists of three major components: the cardinality estimation component, the cost model, as well as the plan enumeration component. In order for a query optimizer to select a query execution plan that can execute a query in as little time as possible, the cardinality estimation component and the cost model need to be fairly accurate. However, the cardinality estimation component relies on multiple heuristics that do not contain any information about the data distribution, and this leads to very inaccurate cardinality predictions. And the cost model of modern query optimizers use a hard-coded formula with multiple hard-coded coefficients that are tuned manually by the database admins, and these coefficients do not have any meaning associated with them. So a bad cardinality estimation component as well as a bad cost model coupled together results in multiple suboptimal plans being generated to execute a query. Hence, recent studies have been explored by people in this topic called machine learning for databases, and this has motivated the use of ML techniques and deep learning techniques in the query optimization component of a database. There have been recent algorithms such as the multi-set convolutional neural network, the tree-structured LSTM, the QPPNet, and the query former, and these algorithms are used in the cost and cardinality estimation components of a query optimizer. However, some of these algorithms do not model the tree structured nature of the QEP and hence cannot predict the cost of a query execution plan, and they can only estimate the cardinality of a query. Moreover, some of these algorithms cannot handle join queries, which are seen in everyday use, and they also have very slow inference times and very high training costs, making them infeasible to be used in modern database management systems. So the aim of this project is to design a novel algorithm to predict the cost of a query execution plan. And this algorithm should attain very low errors and also have a very fast inference time and also be very stable when trained with lesser data, because generating training data is a major bottleneck of the training pipeline. However, for this project, we do not consider string predicates and update queries such as insert queries, delete queries, and updating records. So the proposed solution in this project is tree-structured gradient boosting trees, where every node in the query execution plan is modeled as an information vector, and this is passed to the gradient boosting tree, which outputs the cost and cardinality of the node. And these are passed to the higher levels of the query execution plan, where this process is repeated. And finally, the cost and cardinality of the root node is used to estimate the is a final prediction of the query execution plan. However, before we go in depth to explain the tree structure gradient boosting trees, we need to encode the query execution plan in a format that is acceptable by machine learning algorithms. The first step is to encode the operation associated with a node of a QEP. So the operation refers to the step or the algorithm used by the node in the execution plan. These may include scans, sorting algorithms, joins, as well aggregations and parallel operations also. So a simple technique of one-hot encoding can be used to encode these operators. The next step is to encode the metadata associated with each of these operations. And this can be done by using a fixed size 0-1 vector where the bits are set if the associated column or the associated table has been used in the node for its operation. The next important thing to encode is the underlying distribution of the data, and this is done to help the model learn output better predictions and learn the data better. So this is done by selecting a sample from the data set and encode them in a fixed size 0 1 vector where the bit is set to 1 if the uh, corresponding tuple or record satisfies the predicate. And one of the most challenging thing is to encode the predicate. Each predicate can be represented with three vectors. The three vectors are namely the operator vector, the LHS of the predicate, that is the column used in the filter, as well as the right hand side value which is used to filter out records. So to encode predicates, we use a tree pooling algorithm. So all compound predicates may be also compound predicates which consist of multiple atomic predicates. And all these compound predicates can be represented in terms of binary trees. In tree pooling, the vectors are generated for each of these atomic predicates using a neural network. So the different atomic predicates are combined using either the AND semantic or the OR semantic. So what do these mean? So for the AND semantic, we use a min pool node because intuitively it is a good estimate for the number of tuples satisfying the AND operator. And for the OR semantic, we use a max pooling layer. So moving on, we will be explaining the tree structured gradient boosting machine in both the training and inference stages. So the benefit of the tree GBM is that we can exploit parallelism to the fullest, which is a major drawback of other learned algorithms such as the tree structured LSTM. So how do we do this? We can flatten the tree structured query execution plan into a set of nodes along with their cost and cardinality. We propose that only the cost and cardinality of the left subtree as well as the right subtree are required for the model to predict the cost and cardinality of a given node, along with its features, of course. And we do not need any information vector like other algorithms. So this transforms the data into a tabular format, and we can use machine learning algorithms that are very much suitable to tabular data, such as the gradient boosting machines. However, in the inference stage, we predict on the tree structured query execution plan in a depth-first recursive manner, which is the post-order traversal. So the predictions of a node are used as input inputs passed to the parent node, and the final cost is the prediction of the root node. So in this section, I will show the results of the model on the cost estimation task. I'll also show the sensitivity analysis and show how the model performs with lesser training data, and also I'll show the inference times in comparison to Postgres and other learned algorithms. So for cost estimation, our model achieves the lowest mean Q error than other algorithms, and this is a very good indication that the model performs well. And it has better scores on most of the metrics than the other models on the data set. When trained with lesser training data, the model is fairly stable compared to other algorithms, and this is a major improvement because we do not necessarily need to generate plans of so many training data, and this is a very slow step in the training pipeline. And also, it improves the inference time of the model when using less training data. And as for the inference times, the tree structured GBM is significantly faster than the other algorithms. However, it still does not match the speed of Postgres. However, improvements can be made to the inference time by pruning the gradient boosting tree. We can also utilize features that are the most useful and discard features that are not so useful, and this would reduce the training time as well as the inference time. As mentioned earlier, we can use lesser training data to boost the inference time. We could also utilize database cardinalities of nodes that are fairly accurate, like if the database outputs cardinalities of nodes and they're fairly accurate for certain node types, we can use them to replace, and this would avoid multiple function calls to the model, thereby reducing inference times. We could also utilize better hardware to run the inference, such as GPUs, which would definitely speed up the model's inference times. So, thank you for listening. Have a good day.